Thank you. It's a pleasure to be here, and it's so far, and I assume for the rest of the semester, it's been really wonderful to be at the Institute. Whenever I give a talk somewhere, I try to put the little logo, and when I think of IAS, I think of IAS, but when you Google IAS logo, it turns out there are a lot of, these all come up before that, and including the Institute of Advanced Study. Anyhow, you have to talk to Google, I guess. So in any case, what I'd like to tell you about today, there's sort of, I want to tell you a story about symplectic geometry, and I'll begin by giving you a little bit of, remind you some definitions. And the basic idea is that there's sort of two big tools in symplectic geometry, the momentum map and holomorphic curves. And I'll be talking more about the momentum map, but maybe mentioning a little bit where holomorphic curves fit into the kinds of things I'm talking about. And what I'll talk about is how to use the momentum map to make global topological calculations. So I'll tell you a bit of background about symplectic geometry and group actions and fixed points. I'll say a bit about localization with lots of examples throughout. And I'll conclude by saying how the stuff from this part can tell you something about this part. So a symplectic manifold, symplectic geometry is one of these geometries defined by a differential form. So it's a manifold together with a 2 form, and the 2 form is supposed to satisfy that its derivative is 0 and that it's non-degenerate. So that means that at any point in the manifold, your 2 form is something that eats 2 tangent vectors and spits out a number. So non-degenerate just means that if you have a non-zero tangent vector at your point, there is some other non-zero tangent vector that the number you spit out is non-zero. Okay, and so in particular, what that means is that if you take a top exterior power of the 2 form, you get a volume form, an orientation on the manifold. And so the symplectic manifolds are even dimensional, and they're also orientable. So that guy's not allowed. But any surface is a I don't use Beamer. So any surface is a symplectic manifold with any orientable surface with the area form as its 2 form is a symplectic manifold. Okay, and so on R2, I can write down just dx wedge dy. That just means if you have 2 vectors in R2, take their signed area, take the determinant of the 2 vectors, and that is a 2 form. It is one of these forms. It's non-degenerate because we're just taking area. And then in higher dimensions, you could say, well, okay, take the first 2 coordinates of your 2 vectors, take the signed area, take the 3rd and 4th coordinates, and that's what this form does. And the first theorem in symplectic geometry was proved in 1882 by Darboux. He didn't say it this way exactly, but the theorem is this, that you can always choose coordinates locally so that your symplectic form looks like this one. And the reason that theorem is important is that it says that there aren't any local invariants like curvature. So this makes symplectic geometry in many ways very different from Riemannian geometry. The word symplectic is a calque of the word complex. So it was introduced by Hermann Weyl in 1939. In 1939, people were thinking about Lie groups, and one of the Lie groups they were thinking about is the group that preserves a skew-symmetric bilinear form, and that was called either the line complex group or the abelian complex group. It's not an abelian group in the sense that we think of abelian groups, and so this wasn't a very good name. Weyl said, well, okay, just take the word complex and translate it syllable by syllable into Greek, and you get symplectikos. Com becomes sim, and plexus plectikos, so you get symplectic, and that's where the word comes from. Okay, so examples of symplectic. Sorry?
Very interesting.
Huh, yeah. Good, you learned something maybe. Okay. Okay, so compact examples of symplectic. We saw our R2n is symplectic. Your first manifold that you think of, even dimensional manifold, is a sphere, and you say, okay, is that symplectic? It turns out no, that's not symplectic, and the reason is that this 2 form, it's closed, and you can use Stokes' theorem to show that it has to be non-zero and it's not exact. And so that means it represents something in cohomology. So there has to be some H2, some H4, and so forth for a symplectic, compact symplectic manifold. Okay, so that one's no good. But complex projective space, we know that has exactly one degree of H0, H2, H4 up to H2n. And it turns out that is symplectic. That's just the space of all, that's a moduli space if you like algebraic geometry, and that just means it's the set of all complex one-dimensional vector spaces in an n-dimensional space. Grassmannians, which are just the set of all subspaces of dimension k. Flag varieties, which are nested sequences of subspaces. These are all examples of coadjoint orbits or homogeneous spaces, depending on how you want to think. These are all examples of symplectic manifolds, and they're all examples to which everything I'll say later applies. More generally, smooth complex projective varieties are all symplectic. Toric varieties are symplectic. Toric varieties are these nice varieties. Oh, I should have said smooth toric varieties. They sort of have combinatorial data associated to them. An algebraic geometer thinks about a fan. Maybe a combinatorialist thinks about a fan. And a symplectic geometer, you'll see why, thinks about a polytope. And then there are also infinite dimensional, this isn't compact, sorry, but it's infinite dimensional. They're infinite dimensional examples, spaces of loops, maps from a circle into your group that take the identity to the identity. Okay, I should be careful and say maybe smooth maps or some class of maps. Okay, so that has some notion of a symplectic structure. Okay, so lots of examples. Another very geometric hands-on example is the space of polygons. So pol sub d associated to some positive real numbers a1 up to an is the space of, let's see, so I have a moduli space, again, just the set of all polygons with side lengths a1, a2 up to an, space of n-gons in Rd. That's what the d is. So I just have a sequence of vectors. The side lengths are ai, and the sum of the vectors is 0. That just means they come back to the origin. And I want to think about these up to affine motions. So that polygon, that pentagon is the same as that one, or the same as that one, but is different from that one, okay, in R2. And it turns out that the polygons in R3 is a symplectic manifold, but this really depends on the 3. And we'll see why later. Okay, so I want to talk, the talk is supposed to be about group actions. You can ask whether a manifold has any group actions, and that there have been some topologists who say, well, actually having group actions is the uncommon thing, although mostly we think about things that have group actions, so most mathematicians don't think about most things. But, okay, so I want to think about actions that or manifolds that do have actions. So we say that an action is symplectic if it preserves the symplectic form. So if I move around my area, this kind of area measurement under the action, I'm still taking the same kind of area measurement. So we have rotations of a sphere, rotations of a torus. In fact, so on the sphere we have this whole SO3, all of those are good. We have O3 acting, but O3, when I reflect it, if I measure area and then reflect, I'm going to get a negative sign. So that one doesn't preserve the symplectic form. So some are and some aren't preserving our omega. If we have an action of a Lie group, we have vector fields. So if you just look at how the Lie group is acting, and how, say, a one-dimensional or one-parameter subgroup of the Lie group is acting and take a derivative, you get a tangent vector at every point. So this is just saying, for an element of the Lie algebra, look at how it sits inside the group and how it's acting, take a derivative. Okay, so for example, when my circle is acting on the sphere, the vector fields are exactly parallel to or tangent to the latitude lines. And I have 0 at the North Pole and the South Pole, which are fixed. I can see what symplectic means in terms of this vector field, because symplectic means, well, if I take the derivative of omega in the direction of the vector field, I should get 0, because the vector field is, the group action is supposed to be preserving omega. So infinitesimally, that just means that the Lie derivative along the vector field is 0. But Cartan's magic formula is that this Lie derivative is supposed to be, well, I let omega eat the vector field and I take the derivative, and I add to that d of omega plus that one form eating the vector field. But now we're in this symplectic case, so d omega is 0. And so this Lie derivative being 0 just means that if omega eats the vector field and then I take a derivative, I get 0. So this one form is a closed one form. Okay? And I really want to deal with actions where this closed one form is not just the closed one form, but is an exact one form. So the one form is called Hamiltonian if that one form is d of something, d of a 0 form. Okay, you can just think of this as saying the action satisfies some differential equation. So we have this one form is equal to d of a 0 form is just a function. So we have some nice function associated, some nice set of functions associated to our action. And the examples of this we can work out in 2 dimensions. So if we act on CP1, I can write out my 2 form in angle and height coordinates as d theta wedge dh. In those coordinates, my vector field is just d by d theta going around the latitude lines. And then when I eat that into my 2 form, I just get dh, which is d of the height function. Okay, so that one is Hamiltonian. I do have this function. Of course, it's only defined up to a plus, adding a constant, because we're just solving a differential equation. A non-example is the circle acting by rotating the first factor. We can do the same. This is sort of flat in the flat xy coordinates. The 2 form is just dx wedge dy. Say we're rotating the x coordinate, so our vector field is d by dx. Then when I eat the d by dx, I just get dy. And okay, we want to say, okay, that's d of y. But y is this circle-valued thing, not a real-valued thing. So this dy is a non-zero form in H1, and it's not exact. Okay, so this is not one of the Hamiltonian guys. And what I'd like to see is how this Hamiltonian condition is related to having fixed points. So we know at a fixed point, this is 0. And so we have sort of a critical point there. We have this derivative is 0. And what's true is that so a symplectic action in 1959, Theodor Fraenkel showed that if you're in the setting where you not just have a symplectic form, but you have a compatible complex structure, so you're essentially in the setting of a complex projective variety, then this Hamiltonian, this differential equation, solving this, satisfying this differential equation condition is equivalent to having fixed points. Okay, so already it's been known that having fixed points is related to this differential equation. And I should say this was proved in 1959 here at the Institute. Fraenkel was a member here at that time. So the paper from Transactions says from Princeton Institute for Advanced Study. And so our examples, just going back to our toy examples, we have fixed points. In this case, it is Hamiltonian, and this is a free action. There are no fixed points, and it's not Hamiltonian. Okay, another example on our polygon spaces. So remember, this polygon is supposed to be in R3, and I can, if I think about this diagonal, I can think about producing other polygons in R3 simply by rotating these 2 edges along that diagonal. That gives me a circle action. I have fixed points. It turns out I should say this has a compatible complex structure if I choose my A's carefully. And if I choose my A's carefully, this defines a circle action on the entire manifold. And it has fixed points because if I think of just stretching out those 2 edges so that they're lined up, then the action isn't doing anything. So this does have fixed points. That is a Hamiltonian circle action. It commutes with that Hamiltonian circle action, it turns out, and this has a Hamiltonian 2 torus action on it, if I choose my A's carefully so that this is well defined everywhere. Okay. More generally, when there's not necessarily a complex structure lying around, Deuce and McDuff showed in 1988 that for 4 manifolds, this Hamiltonian condition is equivalent to the existence of fixed points. But in 6 dimensions, there are examples that have fixed points, but don't satisfy the differential equation. And it's still open as to whether, so her example has fixed surfaces. It's unknown whether there are examples with isolated fixed points, and somehow isolated fixed points are typically easier to deal with. So, but I suspect there are, but it's not known. And there's sort of another open question about whether circle-valued. So the Hamiltonian condition was equivalent to having some real-valued functions. When you're a symplectic action that's not Hamiltonian, it turns out you have some circle-valued functions, and I don't know whether you can. I mean, the main idea is that those real-valued functions let you do Morse theory, and I don't know whether these circle-valued functions let you do Morse theory. Okay, so if we have a Hamiltonian action, remember we satisfy this differential equation, and combining all of the functions that we get, we can define a momentum map. I lied a little bit. When I gave you the Hamiltonian condition, you actually need a little bit more about the action. You need to assume something about the equivariance of this map, but fine. In all of the examples, we have very good momentum maps. So the map just is a map from M to the dual of the Lie algebra that takes a point to the real-valued function, take a Lie algebra element. Remember, that gives you a function on the whole manifold. Evaluate it at your point P. Okay, so we have some map. It's a map that whose properties we want to investigate. And the first theorem proved about this was proved by Atiyah and independently Gilliman and Sternberg in 1981. That the image is a convex polytope, which is why symplectic geometers think about toric varieties in terms of polytopes and not fans. The image is a convex polytope, and more explicitly, its image is the convex hull of the images of the fixed points. Okay, so we know that the existence of fixed points or the properties of fixed points have something to do with this Hamiltonian condition, and this is in some way making that explicit. Okay, so our example is that we have S2. The image is a not very interesting polytope in one dimension, and it's the convex hull of the North Pole, the images of the North Pole and the South Pole. Okay, much more generally, I haven't told you what the actions are, but there are, well, I told you what the action was on polygon space. Depending on the A's, you're going to get either a rectangle or a trapezoid. For various actions on all of these guys, there are various polytopes. This one I said was infinite dimensional, so that Atiyah, Gilliman, Sternberg doesn't apply, but there's a theorem due to Atiyah and Presley that says that we do have, well, it's not a convex polytope, but it's a convex polyhedral region for a particular action on those loop spaces. Okay, and more generally, I want to think about localization phenomena. So I said after I tell you about group actions and fixed points, I'm supposed to say something about localization, which I want to think of morally as some global feature of the group action that you can describe in terms of evidence of the feature at the fixed points. And so this convexity theorem is exactly that. If I want to know something about the whole polytope, I can figure out what the whole polytope is just by looking at where the fixed points go. Okay, and so topologically, we're going to use some localization phenomenon to describe something global about the manifold in terms of something about the fixed points. Okay, and the thing that we're going to compute, the first thing I'm going to talk about computing is equivariant cohomology. There's a terrible sentence, but I'll tell you what all the words mean. So equivariant cohomology is a cohomology theory, just means it's a functor from spaces to rings. Okay, so it's something that, given a group action, spits out a ring. If I have a map between two manifolds, I get a map backwards in cohomology. I have Meyer-Vietoris sequences, etc. Generalized means the equivariant cohomology of a point is not just Z or R. In the case of a torus, which is mostly what we will be looking at, the equivariant cohomology of a point is a polynomial ring, and the degrees of the generators are 2, and so this is big. The equivariant category means that the spaces that I look at, the maps, should all be equivariant. So if I have a action on M, if I have a map between two spaces, I'm only going to get a map backwards if this is equivariant, and we sort of guess that. Meyer-Vietoris should be with regard to invariant, an invariant cover, and so forth. A feature of equivariant cohomology is that if you have a free action, I mean, somehow the principle is that if you have a free action on a space, the quotient space is as good as the space you started with. So if you started with a free action on a manifold, the quotient space should still be a manifold. And in that case, the equivariant cohomology should just be the cohomology of the quotient. and that's true. And then if we are looking at a compact Lie group G acting, it turns out you can compute G equivariant cohomology in terms of T equivariant cohomology, which is why I only told you what T equivariant cohomology of a point was. It injects into T equivariant cohomology with image Weil group invariants. So there's something, and that doesn't work over Z. You have to be a little careful. There are a few primes that you need to invert. It's not terribly complicated. You just have to be a little careful. Okay, so we want to, so we have the fixed points including into the manifold. That tells us that we get a map going the other way in equivariant cohomology. And the first thing we'd like to do maybe is understand that. And already in the work of Frenkel, it was apparent, but this was, again, in the presence of a complex structure. More generally, Atiyah and Kerwin showed that if you have a Hamiltonian action, then this map in cohomology is an injection. And that tells us that if we want to understand this, all we have to do is figure out what the image is, understand it in terms of computations at the fixed points. And the statement sometimes holds over Z. If the fixed points are isolated, for example, which was the case in all of the examples I put up, then it does hold over Z. And what we have here with isolated points is just a bunch of copies of polynomials. So we can find this as a subring of a direct sum of polynomial rings. And so in theory, the algebraic calculations should be relatively easy. Okay, and so for example, what these look like, if we have a Grassmannian of two planes in C4, this has, so T4 acts on C4 simply by multiplying coordinates. And so we can also shift planes by the T4 action. But the diagonal circle fixes everything. And so there's really a T3. And so that says the cohomology of this Grassmannian is sitting in T3, 6 copies, one for, it's the coordinate two planes that are fixed. And so what a class might look like in the Grassmannian of two planes in C4, say I can look at subvarieties that are all of the two planes that are sitting inside, say, the x1, x2, x3 plane. And that's going to give me a P2 inside my Grassmannian. And I can look at the Poincare dual to that class. And that's going to, when I restrict to the fixed points, give me a polynomial at each of the 6 points. And it's going to look something like that. Okay, so this is just to give you a flavor of what the calculations look like, or what the classes that you're dealing with look like. And so now we get to play around with polynomials. Okay, and the first sort of major progress in this direction is a theorem due to Mark and Bob and Kottwitz that says, well, okay, so in our toy example, what happens if we have a class in here, then we restrict we restrict to the North Pole and the South Pole. We have a polynomial at each. And the fact is that something is in the image of this map, so we can figure out what the image is. It's in the image exactly if this polynomial and this polynomial, polynomials in one variable, if they have the same constant term. So if their difference is divisible by x. And this isn't hard to show. There are a couple ways to do it, but that's what the fact is. And one of the few big theorems in here is that under certain hypotheses, so if you have isolated points, and there's several ways to say this, but if you have an additional criterion that guarantees that you have this sort of pearl necklace of two spheres floating around in your manifold, then in order to figure out what the image of this map is, you just need to look at every pearl in the manifold and look at the thing at the North Pole and the South Pole, look at the difference and make sure it's divisible by something. Okay, so this becomes quickly some very combinatorial or algebraic, commutative algebraic calculation. And so examples, if we're in the case of a flag variety, polynomials will look like this. And for our Grassmannian, we already had something like this. And there have been a lot of people who have used this to say some things. And of course, you can't read that, but I'll tell you a little bit about one of these papers. Okay, so this paper that I worked on as a postdoc talks about generalizing this result to, say, spaces even like loop spaces in a Lie group. So this GKM description works even in infinite dimensional cases. It works for equivariant cohomology that we already knew. It sometimes works over Z if you're a little careful. It works in K-theory, and here I mean topological K-theory. In some cases, this agrees with operational K-theory if you're looking at it from the algebraic side, which agrees with algebraic K-theory for nice classes. And this equivariant K-theory description, say for loop spaces, was known already by Kostin and Kumar in the 80s. And then it's also known in equivariant cobordism. And of course, these examples are only really, I mean, these computations are only really useful if you know what the equivariant theory of a point is. And here we do, and here we do. Here we don't. I mean, well, we do, but we can't really compute. So it's, I mean, this is a theoretical theorem that's what is true is that we understand Euler classes, and that's what you need to understand really the image. But it's maybe of questionable use. But okay, I shouldn't denigrate my theorems, I guess. So, okay. In any case, this has sort of further applications and further thoughts. In Schubert calculus, this has been used by various people to to think about different ways of doing Schubert calculus. I had hopes that this would lead to sort of easier combinatorics, but as far as I know, it hasn't yet. And it does, I mean, you know, in theory, these are all just commutative algebra questions now, so you want to just program them in Macaulay 2 or something like that. But Macaulay 2 really likes quotient rings, and it really hates subrings. So it's very annoying. And if anybody has advice about how to ask questions about subrings, I would love to know. You can do some calculations of Gromov-Witten invariants and quantum corrections. You have to be careful what you mean by quantum corrections or what you mean by equivariant quantum blah, blah, blah. But there are possible ways to do this, and I'll say a little bit about this towards the end. And this has also come up in work of Masuda, Panov, Park, when they were studying something called torus manifolds. This is now in a very topological category. So far, almost everything could be a projective variety, and so it's not saying very much, but theorems like this are true in a more topological context. And actually, one of the things I'm working on this semester with Anarita Piresh is studying toric origami manifolds. What those are, they're a class of something called folded symplectic manifolds. And folded symplectic manifolds, I mean, it's another geometry defined by a differential form. And in that case, the differential form, the existence of such a differential form is equivalent to existence of stable complex structures. So again, this gets into sort of very topological directions, the kinds of questions you ask. There is, in certain cases, we have some sort of GKM theorem, but in other cases, the fundamental group isn't zero. The spaces aren't simply connected. The fundamental group is not like the fundamental group of an algebraic variety. So algebraic varieties, I guess, have to have fundamental groups with even rank, and that's not true here. You can have S1 as S1 cross S3, and so you have fundamental group Z. And the big question, of course, maybe is topologically, can you determine the manifold combinatorially with some, you know, combinatorics up to cobordism? Okay. I am apparently talking very fast because usually I don't get to this point by half an hour in. Okay, so any questions? Okay. So in the last part of the talk, I wanted to say something about symplectic reduction and how these localization techniques can be used to say something about symplectic reductions. So symplectic reduction is the way of constructing quotients, constructing new examples from old ones in symplectic geometry. We have this momentum map, and in the symplectic category, you can use this to prove a lot of the results that I talked about already. And essentially, the reason is that this phi c, these individual functions behave like Morse functions. They're Morse functions in the sense of bot, which just means that they maybe don't have isolated critical points, but they're good enough. Oh, right, and I was supposed to mention, I mean, of course, it's celebrated, right, that Morse was here and developed Morse theory here, except that I was at Cornell recently, and my chair reminded me that, in fact, Morse was at Cornell before he was here, and the very beginnings of his, of Morse theory were developed there, but okay. Okay, so the reason this momentum map is useful is that you can do Morse theory. It's also an equivariant map, and so that means that this level set, phi inverse of mu, any level set, is a T invariant submanifold. And if mu is a regular value, this is just differential topology. The level set is a submanifold. Okay, so you might say, well, is that a symplectic submanifold of our original manifold? And of course, no. It's by differential topology. The level set is dimension m minus dimension t, and we know manifolds, symplectic manifolds, are supposed to be even dimensional. But the miracle that happens is that I can restrict the 2 form to the submanifold, and the directions where it's degenerate are exactly the orbit directions for this T action. And so this, if I quotient out, this thing is even dimensional, and the theorem is that that this quotient phi inverse of mu mod T is a symplectic space, and it has at worst orbifold singularities. Okay, so this is the way to construct new examples. The basic example is this. Look at the circle acting on Cn by just scaling each coordinate. So that's my action. My momentum map for this action just takes a string of n complex numbers to the sum of the lengths. The level set at mu, this is just going to be a 2n minus 1 sphere. And the circle acts on this, and the circle directions, that's just the Hopf vibration. So the quotient is just Cpn minus 1. Okay, so that's a very explicit way to see Cpn minus 1 is symplectic. And Delzant's theorem says that compact toric symplectic manifolds are in one-to-one correspondence with some adjectives applied to convex polytopes. And the way he proves the existence part of his theorem, given a polytope, there is a symplectic manifold, is he says, well, okay, given the polytope, here's a way to take an affine space where n is the number of facets in the polytope, divide it by a torus that is of the appropriate dimension to get a symplectic manifold. It has a residual, so let's see, Tn really acts here. And so there's a residual Tn minus d action on this, and this is the moment polytope for that residual action. Okay, and the combinatorial torics all works out very nicely. I should say these the GKM theorem applies here. The condition that all of these checking for each edge, all of these divisibility conditions, is equivalent to checking that an assignment of polynomials on a fan is a global piecewise polynomial. So there's been a lot of combinatorial work done on the ring of piecewise polynomials on a fan, and that's, you know, in some way just a reinterpretation of the GKM theorem. And so we can, one might hope to understand that combinatorics a little better. Some more examples of quotients. If I have, let's see, so I have a Tn action on a flag variety, on Grassmannians, on coadjoint orbits or homogeneous spaces in general. These quotients are called weight varieties because depending on the symplectic form that you choose on these, and depending on the regular value where you reduce, this tells you something about weights of the torus action of a G action on a, so if you think of a G rep, how do you break it up as a T rep in terms of irreducible representations? And so these are called weight varieties because there's some, there's a deep connection between these quotients and the corresponding representation theory. Okay, so another example, I said that we would see this as symplectic. It's symplectic because, well, we have this description. We have n vectors in R3. They're supposed to have length ai, so that says that we're living in a product of two spheres. This adding up to 0, it turns out, is just a momentum map condition. That's taking a level set at 0. And then we're dividing out by SO3. And so this is a symplectic quotient. And it fits nicely into the Gelfand-McPherson correspondence where, so we can think of this product of S2s as a quotient of C2 to the n, and I quotient by a torus, and then by SO3, I can alternatively quotient by U2 and hit the Grassmannian on the other way around of the diamond and think of polygons as a quotient of a Grassmannian. So depending on how you want to think about your polygons or depending on the kind of geometric calculation you want to do, torus quotients are sometimes easier, and this space we understand pretty well, like this space. So, okay, so cohomology of symplectic reductions. Francis Kirwan showed in the 80s that if we have a compact Hamiltonian T-space, then, well, okay, so we know that the inclusion of the level set is an equivariant map because this is an invariant subspace. So we get a map the other way. And Francis Kirwan showed that this is a surjection. And of course, the point is that when mu is a regular value, this is precisely the cohomology of the quotient. Okay, there might have been finite stabilizers. I don't want to worry too much about that. Just call this what you want the cohomology of the orbifold to be. Okay, so this is possibly an orbifold, and this is its cohomology. Okay, this works sometimes over Z. This is maybe not the best theorem you could prove, but it's sort of the first theorem you would prove, that in certain cases you still get surjectivity over Z. This is much fussier than the injectivity theorem being injective over Z. The technique for both of these theorems is that this, so for the localization theorem, we were just doing Morse theory, basically. Here we're doing something called Morse-Kirwan theory. This map, norm square of phi, that's a map from M to R. The minimum is 0, because we're just looking at norm square. And so the minimum, if the minimum critical set is phi inverse of 0, which is exactly a level set of our moment map. And then the idea is that you have some control of what the other critical sets are. And it's messy. It's not, the original definition in Kirwan's work doesn't even make it look like it's a sort of differential topology kind of thing. It looks like you have some global condition. It turns out that this minimal degeneracy is something that you can prove locally, but even proving that is really fussy. You have to be very careful when you're doing your differential topology. But it is. And the other fact is that this kernel is computable. It was first computed, the kernel, in terms of, in various ways using residues. Lisa Jeffrey and Francis Kirwan computed the kernel. But you can also compute it in terms of localization. Remember, we know this in terms of fixed points. And Sue Tolman and Jonathan Weitzman first showed, and Rebecca Golden refined, that you can describe this in terms of localization. And what I mean by that, so their theorem says something like, the kernel is generated by classes. If I'm taking a level set here, I look at all hyperplanes through my regular value, and I look at the classes that are supported on one side or the other of the hyperplane. If it's supported on one side or the other, I throw it into the kernel. If it's not, I don't, and then I take the span. Okay, and this is it's not obvious. There is an effective algorithm to compute this. I mean, this is not. It seems like you could be doing something horrible, but you're not. Okay, so the algebra of this is relatively easy to understand. And so that, or I should say, that already allows us to completely describe the cohomology of the quotient, at least if we know equivariant cohomology upstairs, which I hope I convinced you that we do. For toric varieties, if you do this, remember a toric variety is a quotient of an affine space. So for toric varieties, this gives you the description of the cohomology as a quotient of a polynomial ring divided by, it turns out, some monomials, and that's the presentation, the Stanley-Reisner presentation of the cohomology of a toric variety as a face ring. Or maybe that's the Danilov-Jerkovich theorem. I'm always confused. In any case, it's the face ring description. and the theorem that I want to end with, and gosh, I'm ending very early. The theorem that I want to end with, but I guess it's better to end early than late. The theorem that I want to end with is this. So if the quotient is an orbifold, toric varieties are usually manifolds, sometimes orbifolds. But if we're in the orbifold setting, then it turns out we can compute. So already Kerwin's theorem plus these kernel calculations tells us we can compute the regular cohomology. If you're in the orbifold setting, there are more refined invariants. So there's something called Chen-Ron cohomology, which is it's the degree 0 sort of stacky Gromov-Witten invariance of your orbifold. And with Rebecca Golden and Alan Knudsen, we showed that there is a surjection. This thing is big. I'm taking a direct sum over all of the elements of the torus. So that's not something you would normally do. Our macro for that in our text paper was \ROUS, ring of unusual size. And so this is maybe not something that's effectively computable, but it turns out that there's always a finite subgroup of T that you can use rather than using the whole torus. So this isn't as bad as it looks. And the kernel is very computable, exactly as it was for Tolman, Weitzman, and Golden. So everything in terms of localization, this becomes a very simple calculation. And it applies to symplectic toric orbifolds. It applies to weight varieties. And it can be generalized to equivariant K-theory, where there's something to prove that there's a surjection in K-theory. That is work of Megumi Harada and Greg Landweber. But then the same kinds of techniques apply to stringy K-theory, I think it's called, for orbifolds. You can do explicit computations in K-theory. And Gonzalez, Woodward, Ziltner, and a number of other people have been trying to understand the relationship between something you might call equivariant quantum cohomology of some space and the quantum cohomology of the quotient. And with Linda Chen and Kaisa Taipale, I've been trying to understand, or this semester I am trying to understand what the quantum cohomology of these polygon spaces should be. At least in some nice cases, these are Fano varieties. So these are the kinds of generalizations. And I was supposed to say something else. Oh, right. So in theory, in theory, of course, one actually wants to do this for cobordism because you know how to compute some kind of cobordism. But as I said, equivariant cobordism of a point is, I don't know how to make norm square of the moment map into a nice function with regard to cobordism, equivariant cobordism. So that seems hard.
Thank you very much.